I have spent most of my life as a physicist, and I have learned that the universe has a way of surprising us just when we think we understand it. We build our theories, we polish them, we admire them, and then nature hands us something so strange, so unexpected, that everything we thought we knew has to be reconsidered. The holographic principle is one of those surprises, and I want to talk to you about it today, not because I have all the answers, I certainly don't, but because I think the questions themselves are worth sitting with for a while. Let me begin with something simple. When you look at a hologram, one of those flat plastic cards that produces a three-dimensional image, you are looking at something genuinely remarkable. All the information needed to construct a three-dimensional picture is encoded on a two-dimensional surface. The depth, the texture, the spatial relationships, all of it is there, compressed into a flat sheet. That is the essence of what physicists mean when they talk about the holographic principle as it applies to the universe. The idea is that everything you see around you, every galaxy, every atom, every thought you have ever had, might be, in some profound sense, a projection, a kind of cosmic hologram encoded on a surface far away. Now, I want to be careful here because physics has a way of being distorted when it passes through the hands of people who are too eager to make it sound more mysterious than it already is. The holographic principle is not mysticism, it is not metaphor. It is a genuine, mathematically precise conjecture that has grown out of some of the most serious thinking in theoretical physics over the past half-century. It deserves to be taken seriously on its own terms, not dressed up in the language of science fiction. The story really begins with black holes. I was around for some of the early debates about black holes, and I can tell you that the physicists who first took them seriously were considered rather eccentric. When I was young, black holes were a mathematical curiosity, a strange solution to Einstein's equations that most people thought had nothing to do with the real universe. We were wrong about that, as we have been wrong about many things. Now, one of the most important questions about black holes concerns what happens to information when something falls into one. This is not a trivial question. In ordinary physics, information is conserved. If you burn a book, the information in the book is not destroyed, it is scrambled, distributed among the smoke and ash and heat, but in principle, if you could track every atom and every photon, you could reconstruct the original book. The laws of physics, as we understand them, do not permit information to simply vanish, but black holes seem to violate this principle. Once something crosses the event horizon, that boundary of no return, it appears to be gone forever. Stephen Hawking showed in the 1970s that black holes actually radiate energy and eventually evaporate. This is one of the most beautiful results in all of theoretical physics. It combines quantum mechanics, thermodynamics, and general relativity in a single calculation, but it raised a terrible problem. If the black hole evaporates completely, what happens to all the information that fell in? Does it simply cease to exist? This question bothered a great many people, including Hawking himself, and the arguments about it were fierce. I watched physicists I deeply admired take opposing sides. Leonard Susskind and Gerard Hooft argued that information must be preserved. Hawking argued that it could be lost. They went back and forth for years. This debate, which became known as the black hole information paradox, turned out to be one of the most productive arguments in the history of physics, not because it was quickly resolved, but because the effort to resolve it led to entirely new ways of thinking about space, time, and the nature of reality. One of the key insights came from Jacob Bekenstein, a young physicist who had the boldness to suggest something that his colleagues initially found absurd. He proposed that a black hole has entropy, that it carries information, and that the amount of information is proportional not to its volume, but to the area of its event horizon. This is a deeply strange result. We are used to thinking that the information content of a region of space should scale with its volume. If you have a box and you double its dimensions, you expect it to be able to hold roughly 8 times as much information. But Bekenstein was saying that for a black hole, the information scales with the surface area. It's as if the interior of the black hole doesn't really exist independently, as if everything inside is somehow encoded on the boundary. Hawking then confirmed this with his own calculations, showing that the entropy of a black hole is indeed proportional to its surface area in units of the Planck length squared. The Planck length is an extraordinarily tiny scale, about 10 to the minus 35 meters, below which our current theories of physics break down. These units are important because they suggest that at the most fundamental level, space itself might be discrete, pixelated, made of something we do not yet understand. Now, if this is true for black holes, the question naturally arises, is it true more generally? Is the information content of any region of space encoded on its boundary rather than in its interior? This is the holographic principle in its general form, and it was articulated most clearly by Susskind and 't Hooft in the early 1990s. They proposed that the universe as a whole might be described by a theory that lives on its boundary, that the three dimensions we experience might be, in some precise sense, a projection of a more fundamental two-dimensional reality. This is where things get genuinely strange. And I want to pause here to say something about strangeness in physics, because I think it matters. One of the things I have tried to tell young scientists throughout my career is that strangeness is not a reason to reject an idea. Quantum mechanics is strange. The special theory of relativity is strange. The idea that the Earth moves through space at enormous speed is strange, if you have never thought about it before. Strangeness is not a defect. It is often a sign that we are getting close to something true. The holographic principle became much more concrete in 1997 when Juan Maldacena, a young Argentine physicist working at Harvard, published a paper that has since become one of the most cited in the history of physics. Maldacena showed, in a specific and mathematically precise context, that a theory of gravity in a three-dimensional space is exactly equivalent to a quantum field theory, a theory with no gravity at all, living on the two-dimensional boundary of that space. The two theories describe the same physics from different perspectives. This result is known as the ED-S/CFT correspondence, anti-de Sitter space/conformal field theory, and it is a genuine duality, meaning that every calculation you can do in one theory has an exact counterpart in the other. Now, I should be honest with you, the space in Maldacena's construction, anti-de Sitter space, is not the space we actually live in. Our universe is expanding, and it has a positive cosmological constant, which puts it in a different class than anti-de Sitter space, so the precise version of the holographic principle that Maldacena proved does not directly apply to our universe. This is an important caveat, and I think it is worth stating clearly rather than glossing over it in the excitement about the broader idea. But here is why physicists take it so seriously regardless. The fact that such a duality exists at all, that a theory of gravity can be exactly equivalent to a theory without gravity on a lower dimensional boundary, is extraordinary. It suggests that the relationship between gravity and the boundary description is something deep and real, not merely a mathematical coincidence, and it has proven enormously productive. Physicists have used the AD/EFT correspondence to calculate properties of quark-gluon plasma, to understand high-temperature superconductors, to make progress on the black hole information paradox. The mathematics works. The duality is real. Whether it applies to our universe in its full generality is still an open question. Let me tell you what I find most philosophically interesting about all of this, because I think the philosophical dimension is just as important as the technical one. The holographic principle, if it is correct, forces us to reconsider what we mean by space. We are accustomed to thinking of space as the fundamental arena in which things happen. Matter exists in space. Forces act across space. Time flows through space. But if the holographic principle is right, then space, at least in one of its dimensions, might be emergent. It might be something that arises from a more fundamental description that doesn't contain it as a primitive concept. This is a very radical idea. I am old enough to have seen many radical ideas come and go, and I try to hold them with a certain lightness. But I am also old enough to recognize when something is genuinely profound, and I think this is the notion that space might emerge from something more fundamental, that it might be in some sense constructed from the entanglement of quantum degrees of freedom on a lower dimensional surface, is one of the deepest ideas in contemporary physics. There is a beautiful connection here to quantum entanglement, which Einstein famously called spooky action at a distance. Recent work by physicists like Mark van Ramstonk has suggested that entanglement and geometry might be deeply related, that the fabric of space might actually be woven from the threads of quantum entanglement. This is a conjecture, not an established fact, but it is a conjecture supported by a growing body of evidence from the mathematics of ADS/EFT. The idea is that if you take two regions of a holographic space and increase the entanglement between their boundary descriptions, they move closer together in the bulk. If you reduce the entanglement, they pull apart. Geometry is, in this picture, a kind of shadow cast by entanglement. I find this breathtaking. I have spent my life thinking about physics, and I am still capable of being breathtaken. The idea that two black holes could be connected by a wormhole, a shortcut through space, and that this wormhole might be mathematically equivalent to quantum entanglement between the two black holes, this is the kind of thing that makes me grateful to have lived in a time when such ideas could be seriously entertained. Now, let me say something about the limits of all this, because I think intellectual honesty requires it. The holographic principle is not yet a fully developed theory of everything. It is not the final answer. It is more like a powerful clue, a hint that we are on the right track towards something, but that something is still not entirely clear. We do not yet have a holographic description of the universe we actually live in. We do not yet fully understand how to recover the physics of the interior from the boundary description. We do not have a complete quantum theory of gravity that incorporates the holographic principle in a fully consistent way. These are not small gaps, these are fundamental problems, and they will require fundamental solutions. I have spent a great deal of my career being skeptical of grand unified theories that claim to explain everything, string theory included, which is the framework within which much of holographic research is done. I remain skeptical that we are as close to a final theory as some of my colleagues believe. But I also believe that the questions being asked are the right ones, and that the tools being developed to answer them are genuinely powerful. One thing I have always believed is that the universe is not obligated to be comprehensible to us. There is no law of nature that says reality must be expressible in terms that human minds can grasp. We are biological creatures who evolved to survive on the African savanna, not to understand quantum gravity. The fact that we have gotten as far as we have, that we can talk seriously about the holographic structure of space-time, is itself something of a miracle. But I also believe that the universe is richer and stranger than any single theory we have yet devised. I am deeply suspicious of physicists who become too attached to their frameworks, who mistake the map for the territory. The holographic principle is a map, a beautiful and probably very accurate map, but it is not the territory. The territory is what is actually out there, and it will surprise us. It always does. When I think about the holographic principle, I think about what it means for our place in the universe. If the three-dimensional world we inhabit is in some sense a projection from a two-dimensional surface, what does that say about us? What does it say about the experience of being alive, of moving through space, of feeling the wind and seeing the stars? I don't think it diminishes any of that. A hologram is no less real for being a hologram. The image of a flower encoded on a flat surface is still, in every meaningful sense, a flower. What the holographic principle does is remind us that reality is deeper than it appears, that beneath the surface of experience there are structures and symmetries that we are only beginning to understand. This has been true at every stage of the history of physics. The world of everyday experience, the world of tables and chairs and falling apples, turned out to rest on atoms. Atoms turned out to rest on quantum mechanics. Quantum mechanics turned out to rest on quantum field theory. And now quantum field theory and gravity seem to rest on something even more fundamental, something having to do with information, entanglement, and the geometry of boundary surfaces. I do not know where this chain ends. I am not sure it ends anywhere. Perhaps the universe is turtles all the way down, as the old joke goes. Perhaps there is a final theory, and we are getting close to it. Perhaps the truth is something so strange that we do not yet have the concepts to express it. Any of these possibilities strikes me as interesting. What I do know is that we are living in one of the great ages of theoretical physics. The questions being asked today about the nature of space-time, about the relationship between gravity and quantum mechanics, about the holographic structure of reality are among the deepest questions that human beings have ever asked. And they are being asked with tools, mathematical tools, computational tools, conceptual tools of extraordinary power and sophistication. I am in my 90s now, and I have watched physics change many times over. I have seen ideas that seemed ridiculous become established fact. I have seen ideas that seemed certain turn out to be wrong. I have learned to hold my convictions lightly and my curiosity firmly. And when I encounter an idea as beautiful and strange as the holographic principle, the idea that the universe might be a kind of shadow, a projection of information encoded on a distant surface, my response is not to dismiss it and not to embrace it uncritically, but to stay with it, to turn it over in my mind, to ask what it would mean if it were true, to ask what experiments might test it, to ask what it connects to and what it leaves unexplained. That is what physics is. It is not a body of settled knowledge. It is an ongoing conversation with nature, and nature always has the last word. The holographic principle is one of the most remarkable things nature has whispered to us so far. I think we would do well to listen carefully. Thank you.